Good morning, everyone. Welcome to the class. For the last 2 months, we was talking about the basic principles of deep neural network. From today, I'm going to talk about the reinforcement learning. The reinforcement learning is very traditional control theories. Now we're gonna combine the reinforcement learning methodology with deep neural network. In reinforcement learning, that is very useful to find the optimal solution. In real world, in engineering and in business world, there are many cases where we need to make a best optimal solution. In that case, we can use reinforcement learning methodologies. However, there are some cases where the situation is very simple. The cases are small, but in a case where the parameters is so large, it is not easy to make the best solution. In those cases, in reinforcement learning, agent will be replaced by deep neural network. So it is a little bit complicated. So we need to understand the basic principles of deep neural network as well as the reinforcement learning algorithms. So it is a little bit higher level than previous classes, but be patient, let's move on. The first step to talk about the reinforcement learning is Markov decision process and Bellman equation. Markov decision process is a kind of requirement to be on to apply the reinforcement learning methodologies. When we are applying reinforcement learning methodologies, there is a Bellman equation that is very useful equations. Repeatedly, we're going to use this Bellman equation in algorithm. Also, when we are doing the backpropagation, also we're going to use this Bellman equation. So because of those backgrounds, today I'm going to deeply talk about what is Markov decision process and Bellman equation. This will be the very fundamental stepstone to build up big high story building of deep reinforcement learning. Let's review the previous classes using these slides. I listed up 23 keywords in machine learning. I think at the beginning of this class 2 months ago, we may know these keywords or we may not, but let's talk one by one each time. Now we understand what is perceptron, and we know that what is weight. During the backpropagation, we update the weight until we found the optimal deep neural network. Also, we know what is activation function. Activation function is a nonlinear function in perceptron. Depending on different applications, we use the different activation functions, such as Lello function, sigmoid function, and tangent hyperbolic functions. Also, at the last stage of deep neural network, to define the loss function, sometimes we use the softmax function, sometimes cross entry function, or sometimes mean square error function. One of these functions will be used to define cost function, and that will be used to update the weight parameters. And also we know that what is the meaning of forward propagation and regressions. When we are doing the backpropagation, to find the optimal conditions, we used gradient descent method. And because it is multi-layer structures, it is useful to derive chain rules to apply the gradient descent method. And all these processes are defined as backpropagation. sometimes our network is too much complicated, and sometimes we may have too many data. Sometimes we have to cut it down to make a simple and fast DNN, so we can use the dropout methodologies or overfitting method. In sequential data case, such as RNN and CNN, we had exploding and vanishing problems. Because of that, we remember that recently we are using the transformer learning method that was applied to GPT-3 and BRT. Those models, deep neural network models, are very useful for interpreting and to composing natural languages. And for this kind of sequential the neural network, RNN, LSTM, BRT, GPT-3, backpropagation is named as backpropagation through time because the cost function and all those weights should be updated through backpropagation through time. And it makes the backpropagation a little bit difficult. Also, when we are classifying the images, we know that we can use the CNN and the variation of CNN model. Still, it is very useful, a basic structure of to recognize the images. And during the mathematical the process of CNN model, we know that there is a convolution process and the pooling process. And there are matrices to apply the convolution, and then matrices are called filters. Also, we studied the generative models such as GAN, Dicision, autoencoder, and cycle GAN. And in order to make more precise learning, recently we are using the attention and also this GAN, Dicision, autoencoder, cycle GANs are generative models. And this BRT, GPT-3 are used for natural language processing. And especially in GAN model, we remember that there is a G vector that is called latent vector or G vectors. These are very short summary of the deep neural network. I think these are the keywords in deep neural network. If you can understand right now, and also you have very good concept of these wordings, you are very good to move on. Now let's talk about reinforcement learning. Reinforcement learning is a little bit complicated than the basics of DNN. I listed up some keywords of reinforcement learning. Don't be pressured to understand that, but after 2 or 3 weeks later, we can talk about these keywords again, and at that time, we will have very good ideas of this wording. One of them is action, reward, return, state, environment, discount vector, agent, loop, sequential event, control. Probably I may write down one more prediction, and Markov decision process, Bellman equation, or here it comes back again, prediction, control, value, I think, and then optimal value function, state value function, action value function, policy function, optimal policy, on policy, and off policies. These are more than 20 new keywords, but don't be afraid because I will slowly explain the meaning of these keywords. If you have good idea about this, we can build up reinforcement learning and we can easily discuss. These are not all. That is part of the difficulty of reinforcement learning. Also, I expect you to understand these concepts before the end of this class. Value network, policy network, dynamic programming, policy iteration, value iteration, episode and sampling, Monte Carlo method, temporal difference method, SALSA, Q-learning, reinforce, actor critique, exploration, exploitation, greedy, Monte Carlo tree search, planning, model-based agent, model-free agent, policy gradient. Probably in 3 weeks, I'm going to complete the whole classes in this semester. At that point, I will come back again to talk about these new keywords in reinforcement learning. And those are my class targets. At the beginning, I remember I studied reinforcement learning about 2 years ago. At the beginning, I was really had hard time because my background is semiconductor design, and this is completely new concept used in control theory. And there are a lot of books to talk about this. So it takes some hard time to me. But once I got clear idea on this, I was really happy, and I hope our students can do that with me together. Now, I'd like to talk about the significance of reinforcement learning. It is not important. We don't need to spend this very precious time of May and June to talk about this, to spend time in this class. These are list of the things I really believe that this is why reinforcement learning is important. Number one is it helps to make optimal decision. In our life, there are many cases we have to make optimal decision. However, the model is, if that is like a Go play or Atari game, or there are many cases in engineering or game world, the problem is very, very complicated. Then by combining the neural network with this reinforcement learning, we can make best decision. So AlphaGo can compete with any human Go player. That's because they combine deep neural network, because that is very complicated problem, but also they use reinforcement learning because this is a way to make an optimal best decision. Of course, requirement is computing power, because it is based on the deep neural network. There will be a lot of computation of matrices and nonlinear functions and differentiations. But also, to make a best decision, it will try many different cases. There will be a lot of iterations during this reinforcement learning. So because of that, we need computing power. And also, it is good for business, finance, engineering, game, and investment. There is no limit. Personally, I believe artificial intelligence can replace our human brain. Sometimes it can make a good classification, recognition, or sometimes it can make an art or music. But in many cases, human can make very good decision, and sometimes not. But when making decision, activity can be replaced by deep reinforcement learning. These are the examples. Also, it can make a strategic decision, and it can replace humans' very important capabilities. What is condition for success? Computing power. Because later on, I'm going to talk about Monte Carlo tree search and loops and iterations. When we are applying the Bellman equation and Monte Carlo method and temporal difference method, those are the main focus of the lecture today and next week. There will be a lot of iterations. That means computer has to be able to calculate very fast. That is the and sometimes computer is not fast enough. Then thousands of computers are working together to make a fast decision. And also we need to have a very good model accuracies, especially in the engineering world. Uh, in reinforcement learning, reward is a very good concept to make a best optimal decision, and we have to calculate reward. And sometimes we can calculate reward using the Bellman equation combined with Monte Carlo method and temporal difference method. But in engineering world, we can calculate using the simulation, such as HSpice and so on. Simulate and also ANSYS, ADS. This kind of RF in RF or synapses, depending on whether you are working on chip level circuit design or RF circuit design or package design or PCB design, you can use the different simulation machine, and these machines will be very useful to calculate the reward. So in order to make a best optimal decision, the model accuracy will be an important requirement. Also, a difficult part is that the environment itself should be uh, the Markov decision process. Later on, I will explain what is the requirement of Markov decision process. Such games are easily the Markov decision process. And when you start to think about the deep reinforcement learning for your problem, you have to think about your problem is Markov decision process. Or you can change your environment, simulation or real environment, to be a Markov decision process. So today's lecture will be focused on what is Markov decision process, and in order to apply this, solve this best optimal decision, we're gonna use the Bellman equation and Monte Carlo method and temporal difference method. These will be the key focus of our class today and next time. Also, we have to define appropriate rewards. In game reinforcement learning, winning is the reward. But engineering world, what could be a good reward? Impedance matching could be a reward, or maximum power delivery could be a reward, or minimum loss of your signal could be a reward, or BRT or error rate could be a way to define the reward, or eye opening of high-speed I/O circuit could be a reward. So to be a good, if you want to develop very good reinforcement learning model, you have to design your environment, and that should be Monte Carlo Markov decision process. And also you have to define a good rewards. And also you have to find a good path search method. And reinforcement learning is a method where you try many different cases and find the best decision. So you have to find the best search method. And at the end of class, we're gonna talk about Monte Carlo tree search is one of the method. And anyway, I would like to emphasize that this reinforcement learning is a good way to make a best decision in many worlds, many areas, such as business, finance, engineering, game, and investment. But important requirement is that we have to have a computing power and model accuracy. Also, your problem has to be Markov decision process, and you have to make a good definition of reward. I think this slide, this number 4 slide, is an overall summary of reinforcement learning. And probably at the end of class, I'm going to come back again to talk about this again. Now, what is deep reinforcement learning? I have one more wording here, deep. That means we're gonna combine deep learning with reinforcement learning. And deep learning is coming from machine learning. So in the previous classes, we was talking about CNN, RNN, LSTM, GAN, and transformer learning in GPT-3. Those are the deep learning models. Now we have different algorithm called reinforcement learning that is very traditional control theory to make an optimal solution search. And by combining this, I would like to introduce deep reinforcement learning. And especially in deep reinforcement learning, agent in Markov decision process, there is an agent. Agent will make a decision. And we're gonna, in our class, agent will be represented by deep neural network. Usually agent could be a human being or computers or whatever, but in this class, deep reinforcement learning, agent will be represented by DNN. These are another view of deep reinforcement learning. Now, let's step one more into the reinforcement learning. In reinforcement learning, we have agent. Agent will make a decision. And there is an environment. In game, Go, plate could be an environment. There will be a rule and the game rule itself and structure. It has 19 by 19 grid and it has a black stone. It has a white stone. And it will be a sequential game. And there will be a rule. This kind of thing is called environment. Usually agent is a human being, but in our case, in our deep reinforcement learning, this agent is represented by deep neural network. For example, in Go games, our input is the image of this Go plate game at the current state, and output will be the next action that will be 19 by 19 grid array. And agent will make an action, AT, that is, action is the next stone position in Go play. That is called action. And then this environment, the state of this Go plate game will be changed. And this current position of black stone and white stone is called state, ST. And there is a return. Return means the probability of the winning the game. Probability of winning the game. And later on, we will also define return. That is the future return. That is called return. Okay, return. So by doing this iteration again or again, agent will find a policy that has the best winning rate. In deep neural network may have two different network. One is policy network, the other one is value network. Probably next week, I'm gonna explain more details about value network and policy network. And this agent represented by DNN may have parameters. This parameter has to be optimized to make a best decision, and we're gonna apply the gradient descent method, gradient of policy network or gradient of value network. By applying the gradient descent method in policy network and value network, we can train this DNN, and that is agent, as smart as possible. So once again, I would like to summarize what is reinforcement learning. In the reinforcement learning, we have agent that is actually making the decision. And in our class, agent will be represented by a deep neural network. There are two different types of deep neural network. One is policy network. Second network is value network. I'm 100% sure that after 2 or 3 weeks, we can freely talk about this. Right now, it is really beginning. You may have some hard time to follow. So once again, in the reinforcement learning, we have agent that who is making the decision. Second element is environment, that is defining the rule and the players and sometimes like that. In Go game, it could be 19 by 19 array and black stone and white stone and game rule and that kind of things. And also what is probabilities of uh, white stone and black stone. What is the sequential or pattern? There are many different environment. And environment, from the environment, we can define state. In Go game, it is a image of black stone and white stone in 19 by 19 array. And also we have fourth element of reinforcement learning is the return. We have to decide what is return. In Go game, it is the winning probability. And probably if you design reinforcement learning for stock investment, return could be the income increase. In engineering world, return could be eye-opening margin or BR rate or impedance matching, or you can define it using Smith chart, or there are many different ways to define the return. When agent is making a decision, that is called action. So there are four important concepts in reinforcement learning. One is agent. Once again, one is agent. Second is the environment. Third one is state. Fourth one is return. Fifth one is action. Repeatedly, again and again, I'm going to use these key words. So you have to have very good idea about these five concepts in the reinforcement learning. And we're gonna put this, we're gonna build up next concept on the top of this. So you should have very good idea on that. And one more thing I would like to emphasize at this moment is that in our class, agent will be represented by deep neural network. There are two different types of deep neural network, policy network and value network. And when you are training and applying the backpropagation, we have to define the deep neural network parameters. I think this is a weight. And mathematically, we are describing it as theta W. And by applying the gradient descent method, we can update this theta W. If we update theta W more and more, this DNN will be smarter and smarter. And there will be larger number of loop iteration to make it smarter and smarter. And that is the responsibility of computer. Now, this is reinforcement learning basic concept. But in order to apply the Bellman equation, that is very important mathematical background to make a best decision and training, there is a condition called Markov decision process. If your problem is not aligned with Markov decision process, or if your problem does not meet the requirement of Markov decision process, you cannot solve your problem using reinforcement learning. So when you are designing this environment 1, 2, 3, 4, 5, you have to meet when you are designing this reinforcement learning problem using number 1, number 2, agent, environment, state, return, and action, it has to meet Markov decision process condition. So when you are designing reinforcement learning, you have to check it whether your problem meets Markov decision process. Let me slowly explain what is Markov decision process. Number 1, we have to define state. State is a sequential S0, S1, S2, and S infinite. Sometimes it may have such infinite, or sometimes it has such number. If your state is infinitely going on, later on I will tell you that we can apply Monte Carlo method. If the state has finite number, probably we can apply, finite number, we can apply the Monte Carlo method. If it has the infinite, we can apply temporal difference method. Depending on whether this state is infinite or finite, we can use the different method. For example, in Go Play, there are maximum number of states. But in stock investment, we don't know when the stock market will be terminated. It will go 1,000 years or million years. So definition of state is very important step to start to design the reinforcement learning. So for example, if you are designing robot, S can be represented by a vector such as motion, movement, direction, or position, or battery, or room. Maybe there might be 1,000 vector elements to define the state of a robot. In automotive vehicles, also we can define the state of current automotive vehicle using a vector. It may have 1,000 elements, including motion, movement, direction, position, and room, and road condition, and also road and signals, and also there might be 100 cameras. Input could be vector or tensor. So to start with a Markov decision condition, we have to define state. Second very important requirement is that future of state will be determined by current state. That is, probability of transition from current state S to S dash is totally determined by current state ST. For example, if you have a robot, when you are making decision to move on to next step, if you don't care about what has been done past, your current movement, position, energy is of state that will make a next step. In Go Play, especially in Go Play game, It is really Markov decision process. Current state of 19 by 19 array with Blackstone and Whitestone is good enough to make a decision to make a next stone position. We don't need to know about how it build up the current state. So in that regard, Markov decision has more importance to future and current state, and they neglect the past state. This is a most important condition to apply the reinforcement learning. That condition is called Markov decision process. Most important requirement is that if you want to decide the next state, what you need to know sufficiently is the current state. You don't need to know st minus 1, st minus 2, st minus 3, and something like that. In our human relationship, also, it is good to forget what he has done before. You don't need to remember the emotions related to what he has talked, what he did yesterday or the day before. After sleep, please forget that and start again. So that is called Markov decision process. Oh, the second, I'm sorry, Markov decision process, and probability of this is probability of next state is totally determined by current state. This is the Markov property, and transition from S to S dash is represented by probability S to S dash. And this probability is totally depending on the current state. We don't need to worry about S1, S2, S up to ST minus 1. Forget about that. Only we have to think about current ST. Probability of state ST plus 1 is totally determined by ST, current state. That is the meaning of third requirement. And also in Markov decision process, we have to define reward. Reward is expected reward at state ST is S. So there's an expected value. Expected means that it has certain probability, and it is stochastic probability, stochastic process. Reinforcement learning in some cases is deterministic. At certain state, you make certain decision, but in most of 99% of your reinforcement learning problem is that you can make decision 1, or you can make decision 2, or you can make the decision 3. And depending on different making the decision, or if you make a decision, you will reach to different state. And depending on where you reach the different state, the reward will be different. So there are probability distribution of action. Because of that, reward has also probability. So that's why we have expected value here. So expected value of return is called reward. So when we are defining a Markov decision process, we have to define state, probability from S to S dash, and reward, and discount factor, discount factor. So our total return is the future next step reward plus reward of next step, reward and next step. And up to the end of the episode, this return is the accumulated reward of future. Next state, T plus 2 state, T plus state, 3 state, and T plus N state. But future, accumulated future reward will be contributed to total return, that is called GT, with the discount factor. Sometimes discount factor is 0, and then we said that only we look at the short-term vision, short-term reward. And if the discount factor is 1, we look at long-term reward accumulation, and that total reward will be added to return, and that is called long-term vision. I'm sorry, it is a little bit complicated step. It becomes a little bit more and complicated. Um, so let's explain again. When you are defining reinforcement learning, we have 5 basic building block. One is agent, who is making decision, and action, next state. Action will determine the next state, and we have an environment that is defining the rule of game, and also to make a best. And inside this environment, we can define the state, and we will define the return to make a best decision. These are 5 requirements, especially to apply the Bellman equation. That is very useful equation to build up the mathematical background of fundamentals of reinforcement learning. Also, that will be used for backpropagation of deep neural network agent. In order to apply the Bellman equation, we have to meet Markov decision process. And most important requirement is that if you define the state, probability of future state, what is next state, will be totally determined by current state. When you are making the next state, current state is good enough information. You don't need to go back to the past. That is a little bit good to me, because my character is usually, I'm not looking back. I'm usually more looking at my future, my student future, and my society future. Sometimes I would like to forget about the past, good memory, bad memory, and so on. But I'm looking at the future. And current, today is important in Markov decision condition, and future is important. Today's information is good to make a decision tomorrow. And when you are designing state, this state has a good amount of information to make a next state. So when you are designing state in reinforcement learning, it has to have a good amount of information. If let's assume that we want to make a reinforcement learning for robot, it has S state. It could be a vector or tensor. It has to have information about motion, movement, direction, position, battery, room, condition, and road or signals or sensors. All the information has to be included in the state. So in order to apply this reinforcement learning, you have to be able to make a good design of state vector. And then you have to check it whether the state vector has this Markov decision property, where that probability of next state, st, will have a transition to st plus 1 sequentially. It is true in Go game, and it is true maybe in some engineering problem. And when you make a probability from st to st plus 1 is totally determined by current state. You don't need to worry about the past. That is condition of Markov property. The transition from S state to the next state is represented by PSS dash. We're gonna use this probability again and again, because sometimes we know this probability, sometimes we don't know. So in some way, deep reinforcement learning is to find the transition probability from S to S dash to maximize the reward. This probability we don't know, but during the training in reinforcement learning, we try again and accumulate experience. Sometimes we are using the Monte Carlo method, sometimes temporal difference method. We accumulate experience, and to find the transition probability S to S dash, which can give us best reward. That is the purpose of our deep reinforcement learning, and that agent will be described by deep neural network. After certain try and study, we found the new probability of S to S dash transition. That information will be used for backpropagation of deep neural network. This probability of S to S dash will be used for policy network calculation or sometimes value network calculation. Now, reward is an immediate gain. When you are moving into S to S dash, there will be return, winning probability or some money or something like that. If you invest your money in stock market, today's gain probably considered as a reward. But however, after 10 years, you have to add all together, gain and loss, and accumulated reward is called return. When you are designing your reinforcement learning to maximize this reward, sometimes you can design this, but sometimes you can design your reward to maximize the return. Return is accumulated future return. Current state, next state, next state. Total reward can be added to define the return. Sometimes you can optimize your deep neural network to maximize reward or sometimes to maximize the return. Return put more emphasis to future contribution. Even though we gain $100 today, tomorrow maybe another 100, another 100, another 100. That is good. After 100 days, we may have $10,000. But if you only use the reward, today if you gain the $1,000, you forget about tomorrow and or day after tomorrow, something like total will be just $1,000. So return is putting more emphasis on the future return. Now, this is the definition of Markov decision process. When you are designing deep reinforcement learning, you have to check that you are designing state and environment to meet number 1, 2, 3, 4, 5, 6 condition. Otherwise, even though you spend long time to design your software and coding, we are not sure you make a best decision. Seventh concept to talk about Markov decision process is episode. So to train your agent network, you have to gain experience. So Markov decision process is a kind of self-study. You try, gain experience, and that experience will be transmitted to for the backpropagation of your deep neural network. So you start from state S0, you obtain the reward R0. You move on to next state S1, you experience return R1. Now you move on to S2 and you have reward R2 and you go up to the T. This kind of set from S to T, now you have experience of S and return. And from this, we can also calculate the reward and return. This is one set of information, experience. And probably you may repeat again 10 to 6 or 10 to 9 times or 10 to 12 times. And this experience will be transmitted to training. This set of information to start from state S0 to ST is called episode. So if you have infinite computing power, you can try all the different episodes and gain and more gain and more gain, and your neural network will become smarter and smarter. But because of our life is limited and computing power is limited, selection of episode is very important part of the reinforcement learning. Later on, we will come back this issue again, and sometimes we say exploitation or exploration. And one of the methods we're gonna use the epsilon grid. And later on, and in the especially Q learning, or there are some model-free cases, we're gonna use this kind of method. Now we define state value function. Value function is expected value of return. As I said, that return is if you complete the episode, we know what is the return of current state, next state, and so. Some of this total return reward is called return. Return is expected state value function is the state S expected return. Expected means that there is a probability of action. At state S, we don't know what is the probability of next action, next state. That probability will be trained using the backpropagation and training. But mathematically, we don't know at this moment. Sometimes we know, sometimes we don't know. But most cases, we don't know the probability to be at S. But anyway, if we have a state S and we will have certain S1, S2, and ST. And then at each state, we will have probability. We don't know this probability, so we just try it and we gain the experience. And by having this GT, we have little bit information of total return. And so we have to try many different episodes. So mathematical representation of state value function is the expected value. Once we know this probability of transition, we can calculate. But in many cases, we don't know this probability. And this probability will be represented by DNN. So DNN is kind of probability machine. We don't know what is the mathematics there, what is the logic there, but after training, they make a good decision. Making decision is the probability from S to S dash. That's why we have this expected value that is called state value function. If you have gold plate, let's assume that your next position or black stone position is this position. Why is that? Because state value function of this has the highest number, then we usually put this stone on here. So at each position 19 by 19, the winning probability could be represented by state value function. Total sum of winning probability is called return, and expected, we need to know expected number. Expected return is called state value function. And this state value function will be represented by DNN. Personally, I believe that I have good idea on this kind of concept, but when I'm giving lecture right now, I feel like you may have very hard time to get it. But let's do that. Let's move on to that. As I said that, let's assume you are in state S. You make a decision to this point. That action probability is represented by pi a bar S. This is called policy function. Once again, I said that this policy function is represented by DNN. What would be the position action to make to maximize the winning probability? That probability function, this policy function can be also represented by DNN. You can design reinforcement learning whether you will design deep neural network to represent state value function or policy function or both. Either way, we can this policy network or state value function can help us to make a best decision. When we make a decision action to maximize the state value function, or sometimes we can choose policy action that has highest probability. That is called pi AS. Third important function that is also can be represented by a deep neural network. That is on state and action function. When you are in state S, if you make an action, what is the total return, expected return? That is called state action function. And when you make this action, you follow this policy function. And that's why we put the pi in this equation. If you follow this policy function that is represented by DNN, then the expected return is called action value function. So once again, I would like to review Markov decision process. In order to train your agent that is described by deep neural network, you have to build up episode. Because we don't know what is the inside, what is the probability to make a best decision, we just gain experience. This experience, after you make a million experience, that is applied to the state value function network. State value function is represented by deep neural network. And each state will have different winning probability. That is called state value function. Once you train this state value function, you just follow the state value function who has the highest state number. Then you make the decision to that point. And next week, probably a couple of days, I'm going to explain how to make a state value function and how to train them. One of the method is called SARSA, S-A-R-S-A, and Q-learning, and we're gonna talk about that, and we're gonna also apply the gradient descent method. Second part of the method is the policy network, where we train the probability of action who has the highest winning probability. This policy function will determine the action, and the state value function will determine the best reward return of each state. Sometimes we have both networks, state value function network. Sometimes we have policy network. Policy network, in a case we have to train them, then methodology is called reinforce or actor critic method. And in order to, so I will come back again and to explain more. In order to calculate, or up here, I said we have to update this episode and we have to update the return, total return. But how to make this episode and how to calculate this return, and once you got it, you will apply for training of state value function and policy function network. So how to do that? Bellman function is very useful method. And repeatedly, again, we're gonna use the Bellman equation. So in this class, you have to have very good idea about Markov decision process condition. I had more than 10 condition. Second one is that you have to understand Bellman equation. By combining those two, we can move on to build up gain, and later on we can apply that for training of the policy network and state value function network. First, there are three different levels of Bellman equation representation. Those are the same, but first one is the level 1 value function, the return, expected return when you are following the policy pi. Pi is the probability of S to S dash when you are doing the action A, is the current reward plus future reward. And future reward will be represented by the next step value function. It's a kind of recurrent relationship. So if you want to calculate value function, value is the kind of winning percent or your gain in the stock market. And because policy is stochastic, you have to calculate the expected value. If you know this probability, you can apply this probability into this calculation. Or if you do not know, you try and gain the experience using the Monte Carlo method. So let's assume that you are investing some stock. Today's gain is RT plus 1. Tomorrow's gain will be a value function at tomorrow. Because this value function is the return today and tomorrow, or day after tomorrow. And so if you know what is the return tomorrow, you just add return tomorrow with multiply by discount factor and current return. You don't need to go to the end of the episode. You just try one step and you can feel what is the return tomorrow. That information will be added to your current return. That is the meaning of Bellman equation. And this state action function, action value function, is the return when you are following the policy. And if at state S, if you take an action at T, what is the return? Tomorrow's return plus a day after tomorrow's return, total return with discount factor gamma. Because here is the summation of today, tomorrow, or day of the sequential and the current. So we don't need to go all the way up to next year or day after next year. If you have good value return information tomorrow, just today and look at tomorrow. That is the meaning of Bellman equation. Second level of Bellman equation is like that. If you want to calculate current return, you have to multiply. This is the action value function. That is the return of at state S with action A, and you multiply it with the probability of action A, and your summation make total action. If you invest today, what is the return? Total return today is the, let's assume you make an investment to Samsung or Tesla or Apple. You may have different actions. Depending action, you have good friend at Samsung, you have a good friend and Tesla. Depending on your relationship, you may have different probability of investment. Total return will be summation of all this probability multiplied with return, and you have to consider all the action. And here is the, we have expected value when you are following the pie. Let's assume that Junsang is investing your money in the stock market, and Junsang's policy is depending on how many good friends you have in Samsung, SK Hynix, or Tesla, or Apple, or Google. That could be your policy. That probability of your policy is represented pi A bar S. And each action may have different return. And summation of return with probability will be value function. And this is the another representation of value function Bellman equation. Level 1 has the expected representation with the policy pi. In level 1, policy with expected value is represented by probability of your action. And another representation of action value function is that when you have state S, and if you make an action, if Junsang make an investment to Samsung A, and you may have $100 gain today, probably then also you in the future, tomorrow you also have an action that may have different distribution of your investment. You have to consider all the investment tomorrow that is added here. It is a future return. And that is the second Bellman function. And I will close my class today. It is, I will close my class today. And I thought the explanation of Markov decision process and Bellman equation are very easy, but during the class I look at your faces in the Zoom screen and it seems not easy. But I will repeat this basic concept again next Monday, and I will move on step by step. Thank you for your kind attention. I'm 100% sure that if you understand DNN, basic principle, and reinforcement learning, by combining them two, will be very good tool to make a good engineering decision. Thank you.